Hello guys, welcome to Fire Racer Workshop, and in today's video we're going to be covering the CNETER TAPPED Rectifier. Now the exact aim for the experiment you can see on your screen right now, and right now you can see the circuit that we're gonna be making on Multisim. Now this is my second video for the Multisim, and we're gonna go backwards in the experiments because there are multiple experiments that I've not covered on Multisim. Except for this experiment, I've just covered one experiment on Multisim, that is the common base transistors. So we have just plotted the input and output characteristics of the common base transistors on Multisim, and all the experiments for the BTECH second semester for electronics device have been covered in my channel on OrCAD as well as on Tinkercad. So do check out those videos by clicking on the pop-up I button. So you can, first of all, you can just check the playlist for the OrCAD, then you can just check the playlist for the Tinkercad. Now on your screen right now you can see the circuit diagram for this particular experiment that we are going to be doing today on Multisim, and right now you can see the simulation results that we get out of this experiment. So without further ado, let's get into it. First of all, I'm going to fire up the Multisim software. Now if you want to know how to download this software, so just do leave a comment down below. If I just get multiple requests for how to download and install this software for free, I'll make a video for that as well, and I'll surely do, because this is just a really interesting installation process. Now first of all, what we need is components. We'll go to components, and what we need is transformers. So over here in this section right here, you can see something called as transformers. Let's just go to basics, and there might be something over here. You see there's a section for the transformers. We're gonna select, for the center tap transformer, we're gonna select 1P and 2S. That means 1 primary winding and 2 secondary winding. This type of transformer we need for this particular experiment. Let's just place it here. Then we are gonna go and drag our source. So power source we are gonna be requiring is the AC power source, and now this is gonna provide us with the 120 volts and 20 volts RMS and 60 hertz AC power that you usually get at your sockets and all that stuff. So obviously you can just modify it according to your needs, but this is actually okay. Now for this experiment you're also going to require 2 diodes. So for this particular experiment I'm going to be selecting the normal diode. That is, like, this is a basic diode that we use all day every day. So this is the 1N4007 diode that we're going to be using for this experiment. Actually it's a 1N4007 diode. I just say 00. Please just don't get confused by that. So we need 2 of these diodes. So we need it one more time. Let's just place it right here. Now you have to go to the basics and just click on the resistors. Now what we need as a load resistor is, I'll go with a 1K load resistor. It's just better to go with a higher value, because if you are gonna place a capacitor filter and stuff like that, you're just gonna require a higher value. So because you just don't want to make your capacitor insanely large to just like delete all the ripples out of your power supply, so I'm just gonna go with a 1K resistor. It's your choice. You can just go with a 100 ohm resistor as well. There's no issue with that. Now what I'm gonna need is actually what I'm gonna need is a ground. So let's just import the ground. So this is gonna be the ground, and I'm gonna import 2 of these grounds. You'll see the reason why I'm importing 2 of these grounds. So, and actually I'll import 1 more ground for this one as well. So let's just forget whatever I said. I'm just kidding, I'll explain you. So this particular ground will be attaching to the power source right here. And now what you're gonna do is you're just gonna connect both these secondary windings like this in series, and we're gonna connect our ground to this secondary winding. Okay, so you're all set with the secondary winding, and now you're gonna connect your diodes. These are 1N4007 diodes. You can also take the 1N4001 diodes, but the thing is that you have to just be careful that you don't exceed the maximum reverse voltage for these diodes. On your screen right now you can see the datasheet of the 1N400X series diodes, and you can see that these have almost like a rating of like the reverse voltage breakdown, voltage of about 1.5k kilovolts. So we are safe, and we are like well within the limits of the diodes, and I just love this diodes, to be honest, because these are the diodes that I have been using since I was in the 6th grade. So yeah, there's a kind of a connection with these diodes for me. Anyways, so your circuit is all complete right now. You're gonna do one thing. You have to like double tap on this particular tab right here where you just shown these 10:5:5. What you're gonna do is you're gonna change it to 10:1:1. So primary coil number of turns is gonna be 10. Secondary coil number of turns is gonna be 1, and secondary coil 2 number of turns is gonna be 1. So what it essentially will be doing is it will be stepping down the voltage that is on the primary side of the transformer by a factor of 10. So it will, like for example, if you're getting 12 volts, if you're getting 120 volts RMS, like for example in this case we are getting 120 volts RMS, on this secondary side you're just gonna get 12 volts RMS. It's just gonna reduce it by a factor of 10. And over here as well, over here you can get, over here on the primary side you'll get 120 volts RMS, and on this particular winding right here you'll get 12 volts RMS. So in total between these two wires you will get 24 volts RMS because they're just connected in series. So without further ado, let's just attach our oscilloscope as well. And for this particular experiment, I'm gonna be going with the 4-channel oscilloscope because it's just way easier to wire up a 4-channel oscilloscope. Trust me guys, just use a 4-channel oscilloscope, and you would actually need the 3 channels of this oscilloscope for this experiment. And secondly, you are also gonna need one more ground, so I'm just gonna copy paste the ground right here. So let's just attach the ground to this particular terminal right here. So this is the ground of the oscilloscope, and to be like for your information, the oscilloscopes are ground reference based, so they need a reference voltage at the ground. So this is gonna act as a 0. Your DMMs, the digital multimeters, are floating, they just take the floating measurements. They don't require ground, so they can just take the floating measurements. But this is not the case with the oscilloscope. They are just ground based, so they are just ground referenced devices, instruments. So first of all, I'm just gonna connect the channel number A to this output, sorry, to this input. I'm just gonna connect it to the secondary winding, the first secondary winding. The third input of the oscilloscope, I'm gonna be connecting to this particular winding, the second secondary winding, and this B input. Now this is the output of the rectifier circuit that we'll be getting at this particular point right here in our circuit. So this will be connected right here. So this is the B point, and on channel number A and C we're gonna be getting the input for our rectifier, and channel number B will be getting the output for our rectifier. And now we're gonna just color code these wires so that on the traces as well you can see the same color. On the oscilloscope, whatever color you choose for your wires, that is gonna be similar to the trace color. For example, if you're just getting a graph on your oscilloscope, so it is just the color of the graph is gonna change if you just change the segment color of this wire. So I'm just gonna change the segment color of this wire. I'm just gonna go with yellow. Now just select the colors that are a bit brighter so that it's just easier to see while you even take the screenshot. I'm sorry. So go to segment color, and let's just select green for this one, and for this one let's just select, let's see what all colors we have. Let's just select pink over here. So we're all set on this one. So green is gonna be our output, yellow and pink are gonna be our inputs. Now what we're gonna do is, you can also use, and this is a small trick that you can use, if you're on your PC, you can use your scroll wheel to just zoom in and out of the circuit. And also if you just click on the scroll wheel, you can just drag your circuit here and there. So I just use this trick all the time, so I hope you people just don't get confused by this thing. So I'm just gonna drag the circuit to one side of my screen because I want to open up the oscilloscope. Now to see the plotting window of the oscilloscope and all the settings of the oscilloscope, you have to just double tap on the oscilloscope. This is going to open up this window. I'm just going to enlarge it so that you people can see it more clearly. Alright, so over here you need to make a few changes, right? So it's just better if you just make the changes while your circuit is being simulated, but let's just make it beforehand only, or let's just make it afterwards, because it's just gonna tell you that okay, what all you need to set in your oscilloscope and why are you setting those things in your oscilloscope. So let's just simulate a circuit. I'm just gonna click on this one button right here. You can see all the traces we are obtaining on oscilloscope, and these are looking a bit weird. It's looking totally weird. Okay, don't worry about that because this is due to your trigger setting. Now this is called the trigger of the oscilloscope. Now it just tells the oscilloscope when it should like start capturing a waveform. Now you're just gonna keep the trigger to normal. Alright, now you can see the waveforms are just froze in one place and they're just like acting as a standing waves kind of stuff. So this is just set to the rising edge trigger, because whenever the edge will be rising, it's just going to trigger the measurement. If you just set it to falling edge, now you can see on the first channel, on the channel number A of the oscilloscope, you can see when the edge has started to fall. So this is just going to take the measurement. So we're just going to keep it on rising edge. It doesn't matter actually. You can just take it to be wherever you want. So you can also go with a single shot mode. So what it's going to do is it's going to take a single measurement for the, like for example, it's just going to take a single measurement. So after that it's just going to stop, but let's just keep it on normal for now. Now if you want to, now for example, for the channel number A, you know that you're going to obtain about 12 volt RMS value. So that equates to about 16.69 or 96 volts on like peak voltage. So what you need is, this is the channel number A setting. So this is the volts per division for your channel number A. So what you're gonna do is you're gonna increase it so that your trace just fits within the oscilloscope. Now earlier it was at 5 volts per division, so this is one division of the oscilloscope, and you can see over here now this one division represents 5 volts according to the current scale that we have chosen for channel number A. This is for only for channel number A. So if you want your waveform to be smaller, you're just gonna select a higher volts per division value. I'm just gonna go with the 20 volts per division value, because we have to just fit in 3 traces in this particular screen. So let's just do one more thing. The Y position, over here you can see there's an option for the Y position / division. So we're gonna scroll this waveform down to bring it right here, so that we can just clearly distinguish between our input as well as our output. So the Y position can be adjusted by these arrow keys that are provided right here, or you can just manually type it in. So I'm just gonna move it down. So I'm just gonna bring it to the level right here. So over here you can see this is acting as a 0, so this particular division is acting as a 0. Now I'm gonna move to channel number C, because that's our second input. Alright, channel number C is a pink one. So I'm just gonna do the same thing for channel number C as well. I'm just gonna reduce, I'm gonna increase the volts per division, and I'm also gonna scroll it down. Now you can see for the CNETER TAPPED rectifier, what we essentially get, if you just ground this point right here in a circuit, what we essentially get are 2 sine waves that are 180 degree out of phase, and this is being represented really nicely by our oscilloscope right here. So this is these 2 waves are 120 degree out of phase, 180 degree out of phase, I mean. So I'm just now gonna go to channel number B. So this is the output of the oscilloscope. I'm gonna again just reduce it. I'm gonna increase the volts per division. I'm gonna keep it right here only, so this is gonna act as a 0. So this main line over here, this is gonna act as 0. You can also like scroll it up or down a bit according to your taste. So I'm just gonna keep it at 0 only. I'm just gonna keep it at 0 because there's the main trace that we are getting out of our oscilloscope, that is our output. Now secondly, now there are multiple coupling modes for this particular oscilloscope, so you don't need to go into coupling modes, but the thing is, I'm just gonna explain you in brief. So if you just select the AC coupling, it will just remove all the DC components in your signal. For example, if I just select the AC coupling for the channel number B, for example, it is having some DC voltage. You all know that the rectifiers, they produce DC voltage because it's just on the positive. This is only the positive cycle, right? If I just select the AC coupling, it is just gonna bring the waveform right here, so that it's just like the average of the voltage is 0. Essentially it's just 0. If you're gonna 0 it, so it's just gonna short this output, short the input of the oscilloscope. For example, it's just gonna short the channel number B to ground. Let's just keep it to DC for the accurate measurement, and it's just gonna represent how your waveform looks like. So for each and every channel, you're just gonna select the DC coupling. Don't select the AC coupling, because especially for the output. For the input, if you just select AC coupling, it ain't gonna matter much, but don't select it for the input. Sorry, for the output of the rectifier. Now here we come to the time division. So for the time division, if you need to basically view the details of your oscilloscope, you can select the time division right here. So what you'll do is, the scale right here, you can just like increase the scale, so you can see now more of your waveform is being shown on the oscilloscope. If you are gonna reduce it, then you can see your waveform will become like it is just gonna enlarge your waveform, and this is like really good if you want to make like the measurements. For example, if you want to see the glitches in your sine wave, but that is not our purpose, so we are just gonna keep it to a normal value like this. 5 millisecond per division is the best value, I guess, because for the for the voltage source that we're taking and the frequency of the voltage source that we have taken. So 5 volts per division, 5 milliseconds, so 5 millisecond per division. So this on the x-axis represent 5 millisecond on the oscilloscope. So this is what it actually means. Secondly, you also require to take the readings for this particular experiment. So how you're gonna do that, I'm gonna show you right now. For example, now just you can just like stop your oscilloscope for a while. Okay, let's just stop it. So over here you can see all the waveforms are just frozen in time. Now what you're gonna do is over here on your screen right here you can see there are some green lines or something like that. Just go to the top of it and just like start dragging it out. So this is your cursors. So these are your cursors for your oscilloscope. So this one is a cursor number 2 and this one is a cursor number 1. So if you want to measure the peak of your sine wave, for example, obviously you just need a peak value of the sine wave for calculating the DC voltage, the RMS voltage and stuff like that. So what you'll do is, for example, if I want to calculate the peak of your input as well as your output, I'm just going to drag it to the peak of this one. So over here is just going to show me the value that the voltage value that it's just getting that is just getting at the point that we have set the cursor to. For example, this is the T1, that is the cursor 1. Okay, so this is the cursor 1 that we have selected right now. So over here you can see it's just the time is like 4144 milliseconds, and at channel number A we are getting a voltage value of 16.694 volts, and channel number B is at 15.96 96 something volts, and then channel number C is minus 16.649 or something volts. So this is how you're gonna obtain your readings. Secondly, for the channel for this cursor number 2, you can just set it to the for example to the negative waveform. So the negative side, if you need to calculate the peak to peak voltage, for example, this is the positive, this is the negative. So you can just like add these two, like subtract these two to obtain the peak to peak voltage. So I'm just gonna set it to the bottom part of the sine wave. So over here it's just all set, and what I'm gonna do is, like, you can over here also you can see that this is the peak to peak voltage that we are obtaining. Okay, so it's just gonna also subtract. So T2 minus T1 is just gonna apply this operation automatically. You just don't need to do it manually, it will do it automatically. And secondly, if you need to measure the value, the minimum voltage that you're getting at your output, okay, you can also do so by these cursors. So by the cursors you can just measure each and every point in your circuit. So that's how you're just gonna take the measurements for these circuits. Now I'm gonna show you how to add a filter to this particular circuit. Now what we're gonna do is we're gonna go to place, and then we're gonna go to this basics, and over here you can see there are some options for the capacitors. So what we're gonna do is we're gonna go with a 220 microfarad capacitor. So 220 microfarad, why US specifically? Because 220 microfarad is the most available capacitor. It's a readily available capacitor that everyone has. It's nothing to do with the circuit or something like that. It's just like, even like in my lab also, like I have a lab at home, so in my lab also, like these capacitors are the most abundant, and generally we use an electrolytic capacitor for the rectification purpose. So these are the most abundant capacitors. I'm just gonna connect it across resistor, the R1 resistor. So this is the capacitor that we have connected, and now let's just open up our oscilloscope again and let's just simulate a circuit again. I'm just gonna keep the triggers to one side and just simulate a circuit again. You can see now the voltage has just become a perfect, it's just a perfect line, almost a perfect line, not an exact perfect line, but yeah, you can see like the ripples are just like really less for this particular waveform. There are a bit of a ripples, but yeah, they are like almost negligible, so you can just notice that. And that's all for today, guys, and I hope you like this video. Next time I'm gonna be covering the full bridge rectifier and the half wave rectifier, and then I'm gonna be going to the diodes. So the Zener diode as well as the PN junction diode I'm gonna be going to. So stay tuned for those videos, and don't forget to smash the like button and subscribe to my channel. Stay tuned. Bye bye, guys.